Hello everyone, welcome to the 7th video, I believe is what it is, on PID Basics. This is another video in the Digital Eagles programming training series. And so we're going to be talking about PID Basics, and in the past couple of videos I've actually been going super fast, which is, I believe, okay, because those are relatively easier concepts to understand. But with PID, this is something that's a lot more, at least conceptually, challenging for people to understand. And so I'm going to try to take it a little slow on this video. So let's just jump right in. So what are PID controllers? In order to understand what PID is, not PID, looking at you, Henry, basically what that is we need to understand what open and closed control loops are. So an open control loop essentially runs without any feedback. And what I mean by feedback is there's no sort of input, or there is input, there's no sort of input going into the system. And so what that means is it's either on or off. So an example of that would be like a light switch. So when switched on, the light bulb is getting constant voltage regardless of anything. And then when off, the opposite is true. It doesn't get any voltage. So there's no input going in. It's not getting any input or feedback. It's just running whether it's on or off. If you tell it on, it's on. Off, it's off. It's not like it doesn't get any input from like the time of day. So if it's on, it wouldn't be like brighter if it were night or something like that. That would be the input that it would be getting, and then it would be a closed control loop. But the fact that it doesn't makes it open control loop. So a closed control loop, I briefly just described it there, but essentially it runs on a feedback system. It gets some sort of input. And so an example of that would be your AC whenever set to auto. So your AC turns on when it gets too hot and then turns off when it gets too cold. The feedback here being the current temperature, right? So with that, PID controllers are essentially a form of closed loop controllers. They require some sort of feedback in order to operate, and a PID controller essentially has three main parts to it: proportional, integral, and derivative. So if you've never taken calculus, this may be harder for you to understand, at least mathematically. But I should say that once it's implemented programmatically, it's incredibly easy to understand. So why do we use PID controllers? Well, PID controllers essentially allow us to not only create accurate motion profiling, I want to say, but also smooth motion profiling. So basically what that means is, let's take a look at an elevator, for an example. Whenever you ride an elevator, like in a building or something, the elevator usually starts off at a slow velocity, I want to say. So it starts off slow, and then it increases speed, and then right before it's about to reach its target, it slows down, and then it reaches that level and then stops, right? So it not only gets to the floor you want to get to quickly, but also efficiently and accurately, right? So that's essentially what PID controllers are for. They create this curve that allow us to reach a target smoothly, efficiently, and accurately. And so that's why it's important. If we took that same elevator example, and this is actually something that I went through last year in 2019 when programming the elevator. Essentially what I did initially was I counted the encoder counts for the first level, and then I basically said, if we're not there, just keep going, and then once we get there or we overshoot, just stop, right? And so this was okay for a certain amount of time until I realized that the elevator was overshooting the level every single time. And the issue with that was because the elevator just sort of gained momentum out as it was rising. And so as soon as it hit that level, it still had that momentum, and it had to stop with gravity, essentially. Gravity had to slow it down. So that means it overshot it every single time. So what I ended up having to do was account for that by setting the encoder counts to be lower. So I would be stopping earlier, and then gravity would be stopping it at the level that I would want it to be at. Now, obviously, this is very inaccurate and inefficient, mainly because as the strings get loose, it basically won't be in the same consistent environment every single time. And this sort of affects the PID controller to an extent as well. But this makes the initial solution incredibly inaccurate, very inconsistent. And so I ended up implementing the PID controllers later on, and it definitely made the entire system much more accurate. So basically what PID controllers mathematically at least look like is this right here. So we have this output, right? The way we get the output is by having these gains. And these gains are essentially constants. They don't change, they're tuned. And there's a KP, KI, KD. What do they stand for? It stands for K proportional, K integral, K derivative, K being constant, right? So these are gains, and they essentially help us calculate the output essentially. So the final formula looks like this. So there's an output, and that's essentially equal to the error times the proportional. So this is obviously a proportional relationship, right? So this would be the slope m times x, right? So this is mx plus b essentially if you think about it. So that's the proportional aspect. And then here we have the integral. So this is just the error added up over time. If you don't know what the integral is of a curve, essentially it's the area under a curve. So if we took a look at this curve, for example, and we said the set point was the x-axis, right? The integral of this part right here would be this right here, this area right here. And essentially this helps us, it basically tells the PID controller how much it needs to account for to get to where it wants to be. And so that's what an integral essentially is just the area under the curve, helps us get to where we want to be, and then it's multiplied by the integral constant, and then we have the derivative, right? So the change in error over the change in time multiplied by the derivative constant. And so if none of that makes sense to you mathematically, then that's perfectly okay. I think programmatically it makes the most sense. So let's take a look at that. So we're going to start by talking about the proportional component. The proportional value, like I said, is multiplied, is basically the proportional constant multiplied by the error. And so if we calculated our output using only this calculation, that would be known as a P controller, right? Because we only have the proportional portion of the controller. So if we're only implementing a P controller, then that typically solves most problems that a PID controller would need to solve. You can essentially get the desired result you want with just a P controller, but it will take some extensive proper tuning in order to get the proper KP value. Now, having only a P controller can sometimes produce bad behavior, and what that bad behavior would be is essentially this graph. So let's take a look at this graph. So like I said, the set point is the x-axis. This is where we want to be. This is where, let's for example just say x equals 0 essentially. So we want to get to x equals 0, and we start down here. And we start rising. We overshoot just because of how much momentum we had, right? And now we're up here, and now we're pulling really hard to get back to 0, and then we make it. Oh, but we still have momentum. Okay, so we're going down. Now we got to pull back up, and now we're up. Oh, now we got to go back down. So essentially, if you think about this as an elevator, essentially the elevator is just bouncing up and down. It's stuck in this never-ending oscillating state, right? And so if we want to get to this set point here, we're never going to get there if we're stuck oscillating in between, trying to get from up and then it's pulling it down, and then we overshot. Now we got to pull back up, but now we're overshooting again. And so this is essentially what one of the challenges in a P controller is, if not properly tuned at least. And so in order to solve this, we can use the derivative proportion, or the derivative portion of the controller. And so that would be implementing the D part. So then we would have a PD controller. But essentially the mechanism here in this graph is stuck in a never oscillating state, and that's terrible because that means the mechanism will never reach its target. And so, I mean, eventually it will, but it's just going to take so long before it actually does, like before it gets slowed down by gravity, or friction. So we want to introduce the D part of the PID controller, but we'll talk about that after we talk about the integral. So ideally, when it comes to FRC, we want to stray away from the integral. The reason for this is because they actually make the behavior very inaccurate because of something called integral windup. We'll discuss that in the next paragraph, but basically if we introduce the I portion of the controller, then we have now what is called a PI controller, and that's just the integral is essentially the total error multiplied by the Ki gain. Now mathematically, it looks like this with the weird hibbity-dibbity symbol here. But programmatically, it's a lot more simpler in my opinion, which is the error, which is the target minus the actual, right? So where we currently are, this gives us the error. And then we have this total error value here that we're just keeping track of. And every single time we just add on the error, every single time. And this allows us to basically save the sum of all the errors combined. And then we just multiply that by the ki constant, and this gives us the I output, right? So that would be this portion right here, and then we add them all up together. So that would be the I output that it gives us. Now, in my opinion, this obviously is a lot more simpler to understand compared to this. But can you see why this here is a bad thing? Why is this something that we should stray away from? I'll give you a second to think about it. If you want, pause, because I'm going to say the answer in 3, 2, 1. So the fact that the I portion is calculated using the total error over time means that the total error will continuously grow to get bigger. And what I'm referring to is this line here specifically. So because this runs over time, and specifically 0.02 seconds every single time the command is called, it's going to basically increase this total error incredibly large. So if the ki is staying as a constant, right? Ki doesn't change, but the total error increases, then this I output will also increase, which means that this output will also increase. So our output is continuously increasing. And if we have like an elevator or an arm or something, and this is continuously increasing, then that means that our entire mechanism is just going to get faster and faster and faster. And if it gets faster and faster and faster, then that means it's going to be easier to overshoot, and we won't be as accurate. And so that's essentially what integral windup is. It's just the fact that this total error gets so large that it messes with our behavior. Now there are ways to combat this essentially, and we can do that by either capping the I value. So once we get to a certain point, we can no longer let it get larger, or what we can do is reset it. After a certain point, we just reset the total error and set it back to 0. Now, having an I overall in your PID controller makes it very difficult to get consistent results. As a matter of fact, it just makes tuning this right here a bleep. And so if we can't tune in a consistent environment, then it's going to make it difficult to get consistent results, right? And so that's why we want to stray away from using the I part of a PID controller unless we absolutely have to. But instead, we should try to implement the D portion of the controller first. And so the D portion, of course, is this derivative. A PD controller typically solves the oscillation problem that comes with a P controller if properly tuned. It can also solve any steady state errors, which is practically, it provides the output with the final nudge needed to reach the target. What that basically means is if you took a look at this graph right here, this line, it's just below the set point, right? Just below where we want to get. So the derivative would give us that final nudge that we need to get there. But if you've taken calculus, you know that the derivative is basically a way to show the rate of change. And mathematically, it's just the change in error over change in time. But programmatically, it looks like this, which is the error, which is equal to the target minus the actual. And then the delta error is the current error minus the last error, right? So the last error here being some sort of value that we keep track of. And we would have to set the last error equal to the error after we get the delta error. So, or at least we would have to set the last error to the error, so we can basically update this the next time we come around, right? And so we then multiply this delta error by the KD constant, and then of course we would divide by time. Now notice we don't divide by time here. It's not necessary that you divide by time just because of how fast the commands are called in between, 0.02 seconds. So you can divide by time just because of the fact that we know that it runs that fast, so we know what the delta time is, so we can of course divide by delta time if we wanted to, but if you don't, then it's really not a big deal. I don't think you'd notice a big difference, and so it sort of just depends on whether or not you want consistent or at least accurate data. So a majority of PID subsystems will function just fine with the PD controller. However, there's actually one last improvement that we can make that's not as obvious because there's no acronym in the PID. Okay. Anyways, it's the feed forward. And so when using PID controllers, we typically want a feed forward value implemented to combat any guaranteed or at least predicted friction. Now, we can apply this in terms of like the elevator. So if we think about it, the elevator will always face the force applied by gravity, right? That's basically unavoidable. And whenever we want to implement a feed forward value that counteracts gravity, the way we would do that is just by having some value. So the output here being the motor. So we would set the motor to be some sort of value. And we just take a look and see whether or not the slide is moving, right? So if the slide is falling, or dropping at least, then the feed forward value isn't strong enough. If the slide is rising, then it's too strong, right? We just wanted to combat gravity, which means not move. So if the feed forward value is causing the slide to just stay still, then that's absolutely perfect in what we're looking for. And typically you can get away by just making it 0.1. At least in my experience, that's always worked. And so I would recommend just starting with 0.1. Of course, the max value being 1. And so the feed forward basically accounts for that gravity, right? That's what we're combating here. So for example, if the robot elevator is trying to get to a certain level, it'll apply a certain amount of power to get to a certain position based on error, right? So if the error is large, then we're going to have a larger output. But let's say if that elevator is traveling the same error downwards, right? So if we have large error, we have a larger output. But if so let's think about this going upward, right? So if we're trying to go up, large error, large output going up. But now let's say we're up and we want to come down too, right? So we have a large error now coming down. So we're applying larger output coming down as well, but we also have this force of gravity helping us, right? So that means that we'll have that large output as well as the force of gravity, which means in total, our speed will be really, really fast, essentially. So having that feed forward not only combats gravity going up, right? Because now that we're going up, we don't have to worry about the gravity of force pushing us down because that's canceled out. And then we just have that extra output that we have. But then also coming down, that gravity sort of like slows us down and accounts for the gravity coming down, right? And so that basically helps us be a lot more consistent, trying to like use something like an elevator. But this also applies to anything with like guaranteed friction that you could predict or at least, exists. And so that's ultimately the goal that you want your feed forward value to combat. So the final equation, implementing that feed forward looks like this, and the feed forward is just a standalone value, and so it's not really like multiplied or anything. It's just sort of added. So the next thing would be implementing PID controllers into subsystems. So you can either implement it in the subsystems command or the subsystem itself. Now, what do I mean by that? You should never be writing PID controller code at all. You should just be reusing a controller and just implementing it. And what I mean by this line here is just essentially you're instantiating the PID controller in either the subsystems command or the subsystem itself. It doesn't really matter where you're doing it as long as it's called appropriately. So if you're saying that the delta time is 0.02, then I expect the PID controller to be in the subsystems command, or it should be called in the command. It should be calling the subsystem from the command so that it's being called every 0.02 seconds as appropriate, right? But with the WPI library, they actually provide a PID subsystem class, and we talked about that in the command-based programming video. But that class is actually changing in the near future, sooner than you think actually. January is when they'll be releasing the new WPI lib. And from what I've seen, they're making tremendous changes to everything in general. So that'll be something fun for everyone to experience together. But essentially, as of right now, PID controllers, or at least the PID subsystem, isn't very well supported by the community. The community doesn't really like it, and they'd rather make their own PID controllers, rightfully so, just because of issues with integral windup and the lack of sort of support for that. And so a lot of teams like to make their own PID controllers. And we basically have our own as well. And you can find that at this link here. Feel free to look at it if you want. So the next thing is PID gain tuning, right? So we have these constants, these gains. How do we know what to set them at, right? And so this is basically what a PID curve looks like. We have a curve that overshoots and then sort of gets stuck in an oscillating state, and that's what an underdamped response would look like. And in an underdamped response, the gains are too low, which causes the PID curve to overshoot and then potentially oscillate. Here we have a overdamped response. As you can see, it takes forever to reach the set point, which is not a good thing. In a competitive environment, we want to shoot up and then correct ourselves. So overshoot is okay as long as you're able to correct yourself as immediately as possible. And so in this overdamped response here, you can see it takes forever. And then we also have this steady state error where it's not enough. And so the derivative here would help us get there. The next thing is the critically damped response, and here you can see it's actually like perfect, right? So some people may say this is the ideal PID curve, this is what we want, right? And to a certain extent, yes, it's not bad, right? A critically damped PID loop may not be such a bad thing if you don't mind the time it takes to reach the target, right? But when it comes to cycle times and speed, you want to be the fastest on the field. You want to be in and out as fast as possible. And so a properly tuned PID loop should actually look like this, right? So we have an immediate response, which causes slight overshoot, and then immediate correction for that overshoot. And what this would essentially do is the elevator would rise up, slightly overshoot, and then slow back down, and then go back down slowly. That is essentially what we want it to look like. That would be the ideal situation. And so how do we get there? So by tuning, in order to tune at least, I found this helpful source online. If you want to learn more, I linked it here. But essentially all you have to do is set all the gains to 0, right? You increase the proportional gain until you see a steady oscillation, right? Once you see that oscillation, then we increase the derivative gain until the oscillation goes away. Once it goes away, we have what is called that critically damped, curve. And then we just keep increasing the proportional and the derivative as much as possible until the oscillations don't stop, right? And then once we notice that the oscillations continue regardless of whether or not we increase the derivative, then we just set the KP and KD to the last stable values. You just go back one. We say, okay, at this point, we're as high as possible without oscillating. The next thing would be doing the integral if necessary, but I would recommend to stray away from that. So we're just going to pretend like step 6 here doesn't exist, but I included it in case it's necessary. So if necessary, then you can increase the KI gain until it brings you to the set point with the number of oscillations desired. So if you don't mind one oscillation, then bring it up until you get that one oscillation. That's okay. So like I said, this is what the properly tuned PID loop should look like. It should have that immediate response to the target, slight overshoot due to the immediate response and momentum, and then an adjustment to fix that overshoot. The PID loop is ideally fast, accurate, and efficient, and this is essentially what we should aim for. So that concludes the PID Basics video, as well as everything in this course plan. That essentially concludes everything you need to know for this exam. If you have any questions over anything, remember that we are here to help. Please go to the Telegram chat and ask. Do not be shy, or if you are shy, then that's okay as well. Just feel free to message a DTRI and we'll get back to you. Like I said, yep, that concludes everything. May or may not be a next one, but I guess what I could say now is good luck on that exam. See you.